All right, who wants to come up and write the molecular equation? This is going to take a long time. We have to wait this long every time. I'll just give you a little preview. So I'm going to ask somebody to write each part of these three. I think I saw your hand first. No, oh, you're going to point at him. Well, why don't you come up and do one of the ionic ones then? It's terrible. You can rest your hand on the screen. It's not a touch screen. Huh? You can rest your hand. Oh, okay. It's not a touch screen. All right, thank you. What do you think? Good? Great, thanks. That's good to me too. Balanced? All right. Okay, who wants to write the complete ionic equation? Thanks. You gotta go ahead and get the net ionic layer up there. So you got it all crossed out. Thank you. All right, thanks. What do you think? Yeah? Jason, that's all right? Yeah.
Just to clarify, so if it's a solid, you never break it up into two parts?
Right. Because it's not separate ions in solution. It's a solid together. Right. All right, so in the same vein then, let's look at the second one. Aqueous potassium hydroxide is mixed with aqueous iron nitrate to form a precipitate of iron hydroxide and aqueous potassium nitrate. Who's got it? Thanks. You can do as much or as little as you want. You can just do the balanced equation or do the ionic ones too.
Okay. This is weird.
Okay, you could put your hand on it. It's not a touch screen. Right, like on paper.
Out of room.
That's all right. Just go down to the next line. All right, thanks. What do you think? Everybody's happy about this one? Okay. Who wants to write the ionic equations? I'm gonna make some for some really boring video for people following along at home. Nobody wants to give it a shot? It doesn't have to be right. Go up there and draw a tree with a smiley face on it. I don't care. Let's do something.
What if we mess up?
Keep it
It's
going.
on recording.
Yeah, but they don't know who you are. It's the internet.
They can always find out who you are at the end.
They can?
Yeah.
Just with your voice? So don't talk, just quietly stand up from your seat. Move over to the screen. You can bring a friend for support. A couple of you can go up there. I'm not giving up. I'm just gonna stand here. So if you're gonna do anything else today, that's fine. We'll just do a stalemate here. Somebody just go over and write something. I know you know this stuff. You don't even have to do the whole thing. Just do part of it. Hey, thank you.
Like our whole table went.
Right. Yeah, this whole table is running the class right now. Everybody else is just following along, slacking. Yes. Thank you. All right, what do you think? Anybody see any issues with that? We're good? It's good to me. Very nice. Thanks. So who had something approximately like that? No? Something different? Close? What was different? You don't mind. The numbers? Other issues with it? That you did something different? Yeah, so this is right. The only thing that can be a little bit confusing about doing this sometimes is when you have these kinds of compounds, these aqueous ions where there's different numbers of the two different ions, you got to make sure to break those up in the complete ionic equation so that that nitrate ends up being by itself, and there are 3 of them now that they've all split up. And I think the key to doing that right is just to think about what's actually happening. That's showing that that compound started as a solid, but that little AQ means that we put it in water and it broke apart into all its constituent pieces. So if it's FeNO3 by itself as a solid, when it's in water, it's Fe3 plus here, and then NO3 minus, NO3 minus, NO3 minus. And that's how it's then expressed in the complete ionic equation, excuse me, and ultimately the net ionic equation. All right, so then you can do that. Well, good. So next time, stand up and come do it. We'll have some more practice. So I handed out this exam. It's an old exam. It's not mine. I didn't write it, but it's similar to stuff that you might see next week. They're a little shorter. This is kind of a short exam. This was probably when the class was like 1 hour. We've got 3 hours, so it's going to be a little bit bigger exam. But anyway, it's not actually that short. But it's similar to this kind of stuff that we might be seeing. So we're going to go through this later in class today. I'll give you some time to work on it, and then we'll take some breaks and go through some of the questions together, either today or Monday, depending on time, and we'll pull out some more next week so you have a little bit more practice. So you can set this aside. You can work on it. If whatever I'm saying is boring you, you can start working on this instead. But we'll ultimately get to that later. All right, so we've got our complete ionic equations. Yesterday, we did a lot of good chemical reactions, and you saw some precipitates, and you saw some acid-base reactions, and you saw some, what else? Gas evolution, right? And then there were 2 that, well, one that we didn't see was combustion reactions. I guess we saw that on Monday when we lit our Bunsen burners, right? That's combustion. But then the other one that we did see yesterday we haven't talked really about is redox reactions. So let's talk about that now. All right. So we're going to be a little bit more clear and precise about how we deal with charges and what those charges really mean in some different cases. So we talked about things like this, like sodium loses an electron and becomes a sodium ion. Chlorine gains an electron and becomes chloride ion, right? So when we look at this overall reaction, like if sodium metal reacted with chlorine gas, you'd form sodium chloride. And the charges have changed because what we started with were neutral elements, right, elemental substances that didn't have any charges. So sodium metal by itself doesn't have any charges. Chlorine gas by itself doesn't have any charges. And yet when they react, not only do they come together, but now the particles are ions. So now they're charged particles. So what's happened is the electron has transferred from the sodium to the chloride. And in fact, you need two of them. So 2 electrons can go to the 2 chlorine atoms and become chlorides. And that's what's known as redox, or oxidation-reduction. I don't have those definitions here, so we're going to label them. And I know people have different ways of thinking of that, so we'll talk about that. This is called oxidation. And this is called reduction. So, oops, I don't know what I just did. How might you describe that? What is oxidation? What is going on in that reaction that allows us to consider it oxidation? Yeah, it's losing an electron. So we are always going to define oxidation as loss of electrons or electron. It's a little bit confusing of a term sometimes because oxidation sounds like it has something to do with oxygen. And in fact, that's where the word comes from. What we might now call corrosion used to be called oxidation. In some cases, it is oxidation. When iron metal in your car becomes rust, iron oxide, that is indeed oxidation because the iron's gone from a 0 charge or a 0 oxidation state to a +3 oxidation state. But there are other types of corrosion that are not oxidation. For instance, lithium corrodes when it reacts with nitrogen. Or I'm sorry, there are other types of corrosion that are not oxidation. That's not a good example. That is still oxidation. I can't think of my example right now, but let's say plastic being broken down by a solvent or something like that might be considered corrosion, but it would not be oxidation. All right, so then reduction is going to be the opposite of that. Gain of an electron or electrons. And so an oxidation-reduction reaction or a redox reaction is one in which the electrons change from one side to the other. There are only very rare circumstances in chemistry when you can actually just remove or add electrons to something without anything else around. Usually we're talking about transferring electrons from one thing to something else. This can also happen, by the way, with not ionic compounds, with covalent compounds. And that's why we have these two different words, oxidation state and charge. And we kind of use them interchangeably, but they're not really the same thing. Charge really applies to an ion, an individual isolated particle with a particular charge, like a sodium ion. But an oxidation state is still expressed as like a plus or a minus up by the thing, but it's not actually a charge. For instance, in the transition metals, something like chromium, for instance, Cr. Cr can have an oxidation state up to +6. But that doesn't actually mean that it's an individual ion with a +6 charge. That would be an incredibly reactive ion, incredibly difficult to form. And so it actually doesn't form. Chromium plus 6 is surrounded by other elements. It's bonded to stuff. It's not exactly an isolated charge. So really the better term is oxidation state when we're talking about these losses or gains of electrons. So we can do this with something like combustion of methane, even though we don't have metals here to look at. And so we have to assign these oxidation states to figure this out. So we'll actually come back to this once we learn how to assign oxidation states. And that's the other nice thing about oxidation states versus charges, is they also are useful in covalent compounds. Things like carbon, hydrogen, oxygen can have oxidation states even though they're not really charged. They're in covalent compounds. So let's look at how we would do this. Let's look at water. What does the water look like? Anybody know? H2O. H is on the sides and the O in the middle, right? We'll talk about molecular shapes a little later in the semester. So our rule for covalent compounds is that if you've got two identical atoms, like H and H, the electrons are split evenly. If you've got dissimilar atoms, we count the electrons as part of the one with the stronger attraction. All right? So that means that in a compound like H2O, which we're going to talk about electronegativity and polar bonds later in the semester too, so we'll get a little bit more of this. But in something like water, what do you think attracts the electrons more, the oxygen or the hydrogen? If you were to guess. It's the oxygen. So that means that we consider oxygen to have what kind of a charge? If it has the electrons, what charge is that? It's going to be negative, and it's going to be -2, our typical oxide. So we think of oxygen as an oxide, even though in water we know it's not actually ionic, it's covalent. So that means what's the charge of each hydrogen or the oxidation state of each hydrogen in water? +1 to balance out the +2. So, and as this says, these are imaginary numbers. We are tracking the electrons. We are not imaginary numbers in the math sense, just imaginary in that they don't have a physical meaning. We're just kind of tracking the electrons where they are. We're not saying that oxygen is actually a 2- ion in water. We're saying it has an oxidation state of 2-, just so we can kind of keep track of our electrons. So when we go, we'll get to that in a second. Let's go back up here. When we go to something like this does not look like our typical ionic reaction, but we can still assign oxidation states. So let's look at this water that we just talked about. In water, we're saying that the hydrogens are all +1 and the oxygen is -2, an oxidation state, right? You see how we just do that? Another one that we know is that the oxygen in O2 has a oxidation state of 0, because every element in its neutral elemental state, when there's no other atoms around, has an oxidation state of 0. So whether that's O2 or Cl2 or a metal, sodium, whatever, carbon, those have an oxidation state of 0. So what's happening to oxygen in this reaction? It is going from 0 to -2. What does that mean? Does that mean that the oxygen is oxidized or reduced? What? Oxidized? Let's go back up to our definitions. Oxidation is a loss of electrons. Reduction is a gain of electrons. So in this example, has oxygen gained electrons or lost electrons? It's gained electrons. So we would say that it is reduced. It's reduced. So whenever you have a reaction, something has to be oxidized, something has to be reduced. What do you think is going to be oxidized here? We may not know. We'll have to look at it. But let's see if we can figure it out. Let's look at carbon. So between carbon and oxygen, do you know where the electrons go? Which one has a stronger attraction on the electrons, carbon or oxygen? It's actually oxygen. The trend for that on the periodic table is up and to the right. So things to the right are going to have a stronger pull on electrons than things to the left. And that means that the oxygen is going to be -2 And the carbon is going to be what? So each oxygen is -2. What is the oxidation state of carbon in CO2? +4. So let's be a little clear about this. So each hydrogen is +1, each oxygen is -2, and so that means that carbon is +4. And then between carbon and hydrogen and methane, the carbon actually, it's roughly equal, but we could potentially say that the carbon has a little bit more of the pull of the electrons. You know, there's actually a couple ways to account for this. Some people would say that the carbon is -4 and the hydrogen is, each of them is +1. I think that that's reasonable here because it's not oxidized. So we've got 4, or it's not changed over the course of the reaction. So we've got 4 hydrogens, all +1, which means what's the charge of, or what's the oxidation state of carbon in CH4? -4. So if oxygen is reduced, what is carbon? What happens to carbon? It's oxidized. It goes from -4 to +4. So it's lost 8 electrons. Right? And then each oxygen, there's 4 oxygen atoms, and each one gains 2 electrons. So the carbon loses 8 electrons, and the oxygen total, all of the oxygen atoms gain 8 electrons. 2, 2, 2, and 2.
You said that elements with stronger electron attraction are up and to the right. Do you prioritize up or to the right?
Neither, really. We'll get into that when we look at the table of electronegativities. For this kind of thing, it's not that important, but the thing I always remember is fluorine is the strongest. It's called electronegativity, but it has the most of that. So everything kind of trends up toward fluorine. And so your question, like, if you were going to compare nitrogen and sulfur, for instance, right? Because sulfur is closer to the right, but nitrogen's closer up. Yeah. It's hard to make that comparison is really the answer. You have to look it up. All right, so let's go look at the rules for assigning these oxidation states, and then we'll do some practice. So here's our rules. First, the oxidation state of an atom in a free element is 0. We talked about that one. That is should be pretty straightforward, right? It always applies. There's no exceptions that we're going to see. And yet, I see a lot of problems with this with people because they see something like O2, and you get so used to memorizing these ions, and you think, oh, oxide is -2, so the O in O2 is -2. But that's not true. If it's just an element by itself, the charge is, or the oxidation state is 0. 0, 0, 0. Same with H2. We get used to H being +1 all the time. But in H2, just hydrogen gas, it's 0. So we've got to make sure to remember that. Or the counts are going to be off. All right. If you have actually a real ion, remember we talked about the oxidation state is this kind of fake number that's just an arbitrary convention of tracking electrons, but a charge is a real thing. An ion on its own has a real charge. So if we have something like calcium 2+, the oxidation state is 2. Is +2 or 2+, or 2 Roman numeral, however you want to think about that. The oxidation state is the same as the charge when you have an actual ion. All right. And then the sum of all the oxidation states, we've already been doing this with our examples, has to add up to 0 if it's a neutral molecule or a formula unit. Or if it's an ion, it's equal to the charge of an ion. So let's look at one of our ions and see how that works. Let's look at nitrate. Nitrate is NO3-, right? So let's say we want to know the oxidation state of nitrogen in nitrate. We know oxygen is always what in a compound? What's the oxidation state of oxygen? In pretty much any compound? Is always going to be -2. -2, unless it's O2. That's the exception. O2 and peroxide are the exceptions. Everything else, oxygen's -2. So if oxygen is -2, and there's 3 of them, what does nitrogen have to be to balance that out? Not 6, 5. Why is it 5? Yeah, because the overall charge is -1. So +5 and then 3 minus 2 is the -1. That can sometimes be something that slips your mind when you're trying to do these oxidation states. If you have an ion, you add up to the overall charge of the ion, not 0. If it's neutral, you add to 0. Okay. And then there are some that you can always count on. You can always count on group 1A metals, +1. Group 2A metals, +2. We've talked about that, right, when we look back at the periodic table. Those do not change. What is the one exception to that? When would those metals not have +1 or +2 oxidation states? There's only one time. Well, one time that we'll see. There's always exceptions somewhere, but one time that we'll have to deal with. That's when they're by themselves as just neutral metals. And what's their oxidation state there? 0. So if you have sodium metal or calcium metal or cesium metal, that's an oxidation state of 0. But if it's in any compound anywhere, it's going to be +1 or +2 if it's depending on which group it's in. So those are super reliable. Okay. Then we have a little list. This comes from the book. This is not a list of charges that are always this way. This is a list of charges that are likely this way as you move down the list. So let me show you what I mean. If you have, so notice that oxygen and nitrogen are both in this list. Oxygen comes 3rd and nitrogen comes 6th. So that means that if you have a compound that has oxygen and nitrogen in it, you're first going to assume that the oxygen is -2. And then you're going to calculate the nitrogen from that. That's what we did in this previous example with nitrate. We don't assume that nitrogen is -3. We assume that oxygen is -2, and then we calculate the nitrogen. But if it were oxygen and something else that isn't on this list, like some metal or something, then we would assume the nitrogen first is -3, and then use it to calculate the metal or whatever. You see what I mean by that? So this is a list of priorities, meaning that the things higher on the list are more likely to have that charge than things lower on the list. Same thing happened with water. When we put hydrogen and oxygen together, maybe we don't know which one's going to get which charge, which one's going to get the electrons, which one's going to be the calculated one. So you see the list and you say, okay, well, hydrogen's on top of oxygen. So it's more likely that hydrogen is +1. Then we calculate the oxygen, and we actually find that that's +2 also. A good example of where this is not, of this discrepancy is hydrogen peroxide. So if we want to determine the oxidation state of hydrogen peroxide, which one do we do first? What do we do first? If we want to know the oxidation state of each hydrogen and each oxygen, what do we do first? What? Hydrogen, because it's top of the list. So that means we first assign hydrogen as +1. So there's 2 +1s. And then, what do we assign our oxygens to? to balance it out. Yeah, each oxygen has to be -1 to balance that out. Which is weird, because usually oxygen is -2. But because hydrogen has priority on this list, we do that first, and then we calculate the oxygen. And like I said, the only time oxygen doesn't have a charge of -2 is in peroxide or in neutral elemental oxygen. All right, so let's use this. See if you can do this. We already checked nitrate, so let's do a different one. Let's do chlorate. Perchlorate. Do perchlorate, ClO4 minus. Okay, use those rules, specifically that last table, to assign oxidation states to all the atoms in those following three. So you got some oxidation states? Are you stuck? I'm more interested in if anybody's stuck. That's maybe lots of people are stuck in the same place. Would you mind sharing where you're stuck?
For C,
Yeah.
when you put a negative over the O,
Yeah.
is that the charge?
That's the charge of the overall ion.
Overall.
Yeah, chlorate has a
So-
-1 charge.
So you still put O first and do -2
Right.
times.
Right.
Then you check the charge.
So it has to overall, the charges of chlorine and the oxygens have to add up to -1. Other places you're stuck. Nobody else is stuck? Everything's good? Sort of believe that. Somebody's got to be a little stuck, but that's okay. We'll get to it. All right, so CO2 we already did together. Were you able to work through it on your own based on this chart? What did you come up with for the oxidation states? What's the oxidation state of carbon? +4, and oxygen? -2. Yeah. I should also note, I use +4 and 4+ interchangeably. +2, -2+. Have you seen that? I kind of go back and forth between that. Some people like to keep that separate, where the 4+ or the 2+ applies to oxidation states, and the +1 or the +2 applies to ions. I kind of go back and forth. The reason I like the number first is when you're writing it in a formula, it's less confusing, because if you say something like O -2, if there's something else there, it looks like maybe that 2 could apply to something else, and the O is just -1. So that's why I kind of go back and forth. I don't have a rule of when to do one or the other. So I think of them as the same. But yeah, those oxidation states are correct. So you went to the table, you find that oxygen is the higher priority. So that ends up here. Okay. What about SF6? What did you get for that one? So you got that F was -1 and S +6. Right. Again, table F is right up the top because F is pretty much never, almost never ever positive. And so that's going to get the -1. There's 6 of those. It has to add up to 0 overall, so the S must be +6. Note, this is a covalent compound, so it does not mean that sulfur is a +6 ion. This is simply a number that tells us something about the accounting of electrons in this type of a reaction. So that if SF6 underwent a reaction and then became something like SO2, we would say, oh, the S has gained 2 electrons and gone from +6 to +4. All right, and finally, the perchlorate ion ClO4. Cl, what'd you get? +7, right? And oxygen here is -2. So that one has to add up to -1. So we've got -8 overall from the oxygens. That means we need +7 from the chlorine to balance it out. Sometimes things don't follow the rules so well. Like in this one, we're not going to get into that. We could talk about it later if you want, but I don't want to confuse everybody. Okay, so we talked about this reaction already. We went through and did the oxidation states. Often what we do with reactions like this is split them up into something called half reactions. And the half reactions, let me highlight that. Half reactions are what you get when you look just at the oxidation and then just at the reduction. So carbon is the thing that's oxidized. And so that number 1 expresses the half reaction of what's happening to carbon. Carbon in CH4 is becoming CO2 and then losing 8 electrons. So the 8 electrons are going away. And then the other half reaction is the reduction half reaction, where oxygen is gaining those 8 electrons. And when you get into second semester chemistry 122, Gen Chem 2, you'll go through all these rules of how you write the half reactions and how you balance them and all this stuff. We're not going to get into that here. But what we do want to be able to do is determine whether or not a reaction is a redox reaction, figure out what's oxidized, and figure out what's reduced by assigning oxidation states. So that's our goal here. And we've talked about the definitions of oxidation and reduction. I want to look at some really confusing terms now that you see below, which is oxidizing agent and reducing agent, otherwise known as the oxidizer and the reducer, because they're opposite, right? If something is oxidized, it's oxidized by the other thing. So that other thing is the oxidizer or the oxidizing agent. So look at those definitions in the context of this reaction. So once again, just to remember, or just to remind ourselves, what's happening to sodium here? Is it being oxidized? Or it's being oxidized. What's happening to its electrons? Is it losing electrons? Is sodium losing electrons or gaining electrons here? In this reaction? Losing, because it's going from 0 to +1. So it's lost electron. That's what we call oxidation. Oxidation is loss, right? But that means that chlorine, Cl2, is the oxidizing agent. It's the thing that's doing the oxidizing. It is, another way we can say that is, it's taking the electrons from sodium. It might be another way to say that. And so please try not to get confused by this terminology, and you'll get to practice this in your homework and in the book where it will often ask for the oxidizing agent and the reducing agent. If you look up safety information, maybe you did on some of the compounds yesterday, certainly we'll see some in the future, an oxidizing agent or oxidizer can be a hazard. In fact, there's a special symbol in the new globally harmonized system. A flame over a circle is a special designation for oxidizers. These are things that can cause other things to be oxidized. So they are things that tend to want to get electrons, take them from other things. And those types of compounds tend to be reactive in that way, and that's why we keep track of them. Sometimes we need to avoid exposing them to certain types of things like metals and certain types of other compounds. So that could be a hazard, and that's why that's often set apart from other hazards. All right. So let's do one. See if you can do this one. We're going to mix powdered aluminum with pulverized iodine crystals. And you make a big bunch of energy and purple smoke, and I would do it here for you, but it's kind of dangerous. So we could maybe do it in the hood later if you really want to see it. The mixture bursts into flames, purple smoke is produced, and this is the reaction. So I want you to identify the atoms that are oxidized and reduced and specify the oxidizing and reducing agents. But to do that, I want you to also assign oxidation states to everything. So assign oxidation states to all the atoms before you determine, and then look at which way the electrons go and determine what's being oxidized and what's being reduced. All right, go for it. Got some oxidation states? Maybe. All right, what's the oxidation state of aluminum in the reagents, the reactants? 0. How do you know? All right, how do you know? Yeah, because it's just by itself. There's nothing else with it. It's not part of a compound, so it's an element. What about iodine? Also 0, right? So we're taking two things in their elemental states. Okay, then let's look at the compound on the right, aluminum triiodide. What is the oxidation state? How do we assign the oxidation states here? What? The table. So do we see either of those on the table? Which one do we see? Iodine, right. Wait. Oh, right, okay. Yeah, iodine's in group 7A. There's nothing else above it there, so we can assume that that's going to be what? -1, right? So if that's -1 and there's 3 of them, what does aluminum have to be? +3. Good. And really, this is as hard as it gets. Like you assign this, and that's it. So what is oxidized here? What has lost electrons? Who says aluminum is oxidized? Who says iodine is oxidized? Okay. Yeah, it's aluminum. So aluminum is oxidized, which means iodine is reduced. And so what's the oxidizing agent? Yeah, iodine. So that molecule, I2, iodine, is the oxidizing agent. And what's the reducing agent? Aluminum. Because it's the opposite of what's oxidized or reduced. So if something has lost electrons, has given electrons to the other thing, that makes it the reducing agent, because it's given the electrons, it's caused something else to gain electrons. Okay, let's look at, oh, it's not on here. All right, let's look at what we did then yesterday in lab. Anybody know what were the redox reactions that we did yesterday? I guess technically we could maybe call some. No, I don't think so. I think there was clearly just some particular reactions that were redox reactions. Any idea what they were, or what category, what part of the lab in general they were? It was the metal stuff at the end. The metal stuff at the end. So we're going to look at reactions like this and show why. Now we know why. So we put a little piece, you put a little piece of magnesium solid in a solution of, let's say, copper sulfate. And that formed copper metal. You didn't see like shiny copper metal coming up, but I think it kind of turned black, where you had some little black things falling up. That was copper metal. And then the magnesium went into solution. Oops. Okay. So let's look at that reaction. Assign. These are ionic compounds, right? Copper sulfate, magnesium sulfate. So we can assign charges based on that. So first, just to make it easier for ourselves, this can also help you, by the way. If you forget the charge of something, like let's say you know sulfur is SO4. Well, I'll show you how that can help you in a minute. But let's first assign the oxidation states in sulfate ion. So what are you going to assign first? O or S, you think? Probably O, because that almost always has what charge? -2. So if O has -2, then what does S have to have? +6, right? Because there's 4 -2s, and you need an overall -2. So the oxidation state of sulfur is +6. So if you look up at the periodic table, you'll notice that sulfur is in column 6A. That means it has 6 electrons in its outermost level. We'll talk about that in a couple chapters. And if it loses those 6 electrons, or those 6 electrons are kind of somewhere else for a lot of the time, that's what you have in the sulfate ion. So sulfur actually can't have an oxidation state of more than +6 because it can't lose more than those 6 electrons. So if you, sometimes that can be helpful in remembering some of these charges. If you don't remember if SO4 is -2 or -1, you can say, well, if it's -1, sulfur would have to be +7. If it's -2, sulfur's +6. So I know it can't be more than +6. But maybe that's just more stuff to memorize and really not helpful. So you can, that can be your call. All right, so given that, can we assign oxidation states to magnesium and copper? Because that's really what's important in this reaction. What would be the oxidation state of magnesium on the left? 0. And what about magnesium on the right? +2. And that's actually a true charge because that's an ion in solution. And what about copper on the left? +2. And then on the right? 0. So our net ionic equation here, all we break up is the sulfates. And we notice that sulfate is a spectator ion in this reaction. So in our complete ionic equation would look like this. Okay, I think that's right. So the only thing that hasn't changed in this reaction is the sulfate, the aqueous sulfate. So that's our spectator ion. So our net ionic equation is this. And the nice thing about looking at the equation that way is you can really see the oxidation and reduction. So which atom has been oxidized here? Which compound is oxidized? Which one has lost electrons? Magnesium metal, right? Magnesium metal goes from 0 to +2, which means it's lost 2 electrons. And then that means that the copper has gained electrons. So copper 2+ has gone from +2 ion, or 2+ oxidation state, to 0. So that means it has gained electrons. And this is an example of a redox reaction. When you see a change in oxidation states like this over the course of a reaction, that's how you know that you have a redox reaction. That's how you can identify it. So then another thing we did in lab yesterday was check that. Did you have a question? Yeah.
How can you distinguish from the oxidation state and then the ionic charge?
You can't really, except knowing whether or not something is an ion.
Oh.
If something is an ion, if it's in an ionic compound, meaning it's usually a metal, non-metal, but even that is not always true, then you can distinguish that. But otherwise, sometimes you can't. Sorry, I wish I had a better explanation than that. But no, you can't always. So we use them, when we look at compounds, we'll use them more or less interchangeably. So you can calculate a charge, you can calculate an oxidation state, and you'll do it in the same way, generally. Also, we should also note that in the last chapter, when we talked about naming with the metals, with the thing in parentheses, the thing in parentheses is not actually the charge of the metal, even though we said that at the time. It's actually the oxidation state of the metal. Because sometimes those metals are not individual ions, especially when they have really high numbers, high oxidation states. Those are actually oxidation states. But anyway, and then in answer to your question, it's not an important distinction. We can think about those interchangeably at this point. Okay, so let's look at what we did then when you were testing a metal like magnesium. What happened when you put the magnesium, whoops, not zero, solid. What happened when you put the magnesium in acid, say sulfuric acid or hydrochloric acid? Did anything happen? Nothing happened? Nobody remembers? Do you have your notebooks? You can check.
The magnesium.
How?
It bubbled.
It bubbled a lot? And after time, did you see it break down at all, or it wasn't in there long enough maybe to see that? Yeah, so after time, it'll actually totally dissolve if there's enough surface area there. It'll react with that acid and bubble. So what were the bubbles? Most gas evolution reactions we saw before, we were looking at carbon dioxide, but there's no carbon here, so there's no carbon dioxide here. So what are the bubbles? Could be oxygen, because we certainly have that here. But actually, in this case, it's hydrogen gas. So that was hydrogen gas that was coming off of it. And that means that the other part of this was aqueous magnesium sulfate, or perhaps some magnesium hydrogen sulfate, I'm not sure. How fully that reacted. So even though this is adding sulfuric acid, this really was not an acid-base reaction. It's not really a good way to describe this. What's a better way to describe this? That it's a redox reaction, because we have change of oxidation state. So once again, you could compare this to the previous one and see that magnesium is being oxidized. So what is the oxidizing agent then? What is oxidizing magnesium in this case? What is being reduced? Yeah.
Hydrogen.
Hydrogen is being reduced. How do you know?
Because when it starts, it has a oxidation state of +1.
Yeah.
Reactants, and then on the other side, it has an oxidation state of 0.
Right. So we know that sulfate is a -2 ion, right? That means that each of these hydrogens must be +1 in sulfuric acid. And yet the hydrogen on the right side is all by itself, hydrogen gas, which tells us it has the oxidation state of, as you said, 0. So going from +1 to 0 is an example of reduction. You have to gain electron to go from +1 to 0. So the hydrogen is being reduced, and the magnesium is being oxidized. And that's what we saw yesterday. All right, that's a good stopping point. So let's take a break, take 15 minutes, and we'll come back and we'll look at a little bit more practice of this and then head into this practice test and start looking back at some of the other stuff we've done. We'll start a new video.